Hi everyone, this is Mr. Chu and I'm going to go through 9.4 today, which is on resolution. And it is actually a direct follow through from 9.2, which is on single slit diffraction. Why is it that I skipped 9.3? Because it is actually quite a standalone section by itself. I don't know why it is placed right in the middle of 9.1 to 9.5, but 9.3 is going to be a big one and it's going to be something that's isolated. So I leave it to the end. I'll go through 9.4 today, which is on resolution, and it's related to what we learned in single slit diffraction. So let's do a recap. What did we go through for single slit diffraction? So for single slit diffraction, what we have is that when we have a wave coming in, the wave diffracts and it forms this diffraction pattern with the maxima really high and the secondary maxima over here, which is about 1/9 to 1/10 the intensity. You've got to know how to draw this intensity versus angle graph, and we also learned that this angle over here is such that sine theta is approximately equals to sine theta is equals to lambda upon d, and when angle is small, which most of the time when we talk about diffraction it is going to be small. Why? Because when we talk about diffraction limit, usually this is going to be really small and this is going to be really big. So sine theta is going to be really small, and therefore we put theta as approximately equals to lambda upon d. So we learned this. So what's the implication of this? Why is it so important, and what's the link between this and resolution? Now, before I go into the details of the physics, let's take a look at our daily experiences. When you look at a car that's very far away, all of us know that cars have two headlamps. But when we look at a car that's really far away, the two headlamps seems to merge into one. There's some point where if the car were to be too far away, we will not be able to tell two sources as two separate sources. So the point at which we can tell two sources as two different sources is what we call the point where we just resolve the two objects. Now, why is this important in our daily life? It is important because when we talk about telescopes, when we talk about optical instruments, it is important for us to see two separate objects as two separate objects. Imagine that if you were to build a $1 billion telescope and you're not able to tell two stars from two stars, then honestly that telescope is quite useless because you want to see details. If you have a spy telescope and you look down onto Earth, you want to see 5 tanks as 5 tanks. You don't want to see 5 tanks as one big blob of black dot. So that will be really quite pointless if you were to not be able to see the details of what you want to see. So therefore, it is very important for us to know that being able to resolve things is really important. But what limits the point that we can resolve things is what we are going to discuss today. So let's take a look at two stars. Since we talked about stars just now, if you got a star, by right it should form a point image on the CCD sensor. This is the opening of the telescope. It should form a point object, but it doesn't. What it formed is, instead of forming a very sharp point over here, which is a dot over here, which is where the star should be, it forms a blob over here. In fact, it forms rings around it if it is bright enough. Now, another star that is far away will form a maxima over here. Now, this is quite clear cut that you have one blob over here and another blob over here. You'll be able to see two different blobs. Now, that's good because you want to see two blobs as two blobs, because you want to see two stars as two stars. But as the star gets closer and closer, there will be a point where the two stars will just, you barely can make up two stars. And that condition is really important because that's the point where you're just able to resolve the two stars. So that's the point where this happens. Now, this is the point where two objects are just resolved. Now, it is very important for you to remember that it is just resolved, not resolved. As in, it cannot be resolved, neither can it not be resolved. It is just a moment just resolved. It is going from being able to resolve to not being able to resolve. That's the critical point. So, this is the point where the central maxima of one source is directly overlapping the first minima of the other source. And this is Rayleigh's criterion. So it says that Rayleigh's criterion states that two objects are just resolved, again, just resolved, when the central maxima of one source overlaps with the first minima of the other. Now this is in your notes, so I'm not going to emphasize this too much. Now the most important thing is that the central maxima of one source overlaps with the first minima of the other one. So it is important for you to remember this criteria, because this criteria is going to set the minimum separation or the minimum angle that you can still resolve two objects as two objects. So let's take a look. Do you agree that the angle between the central maxima and the first minima of this source A, the angle over here is going to be equal to lambda upon d? Whereas this angle over here, let's call this theta 1, this is theta O, this is going to be, let's call this x and this L. We're going to say that tangent theta 1 is equal to x upon L. But like what I said, most of the time when we talk about resolution, the angle is going to be really small. You don't expect the object to be just in front of you and can't resolve, right? So the angles subtended by the two objects are going to be really, really small. So therefore theta 1 is usually small, and therefore we can say that theta 1 is approximately x upon L. And at the point where they can just be resolved, the angle subtended by this must be equal to this, and that's why we say that x upon L is equal to lambda upon d. Now this is the point where you have to note whether is it a rectangular aperture or is it going to be a circular aperture. Now you have actually rectangular slit or circular aperture. So if it is a rectangular slit, you have to write this, whereas if it is a circular aperture, you've got to remember to add in the 1.22. So most of the time when we talk about telescope, we have to use this instead of this. But in the case where the question is obviously talking about rectangular slit, then you use this without the 1.22. So before we go into examples and show you how this can be used, one of the things I'd like to show you is how does it look like when you have the Rayleigh's criterion. So if you're to go into the Rayleigh's criterion, okay, it looks like there's some difficulties over here in going back to the single screen, where I show you the laptop. There's supposed to be some images, but forget it. I have some difficulties over here. It's okay. So it is in your notes, and you can refer to your notes. There will be two diagrams where it is at this point where it is just resolved. It appears as one block, and where it is two separate blocks. And if it goes any closer than this, it will not be able to distinguish two objects as two objects. It just look like one circular bright area. Alright, so let's try some questions, two questions, if we have time, and that should be enough. So let's take a look. A simple one. So let's imagine if I got a laser beam, and the opening of the laser beam, say it is say 3 mm. So that's where the laser comes out. And we were to point it, the wavelength, say it is 650 nanometers, and we're going to point it at a wall, say at, let's be daring, 1.5 kilometers away. So therefore, for this divergence angle, this is a theta over here because of diffraction. It is a circular aperture, so it is 650 times 10 to the power minus 9 divided by 0.3 times 10 to the power minus 3. That is going to give us an angle of, let's calculate, 1.22 times 650 to the power minus 9 divided by 3 to the power minus 3. That is going to be 2.64 times 10 to the power minus 4 radians. And if you want to find this diameter of the spot, 1.5 kilometers, if it is still bright enough to be seen, then diameter is equals to 2 theta, because it's theta on this side and theta on the bottom side, times L. Why so? Now this is a point of time probably explain a little bit. Remember, you learn circular, measure S is equals to R theta. So in this case, your S is your D, your R is your L, your 1.5 kilometers, and your theta is your 2 theta. So we are assuming that if angle is small, the circular arc is going to look like a straight line. Alright? Therefore, if you compute this, you're going to get the diameter of the spot to be 0.793 meters, which is fairly big, 1.5 kilometers away. Imagine if you point the laser at the cloud, which Probably if it is a few kilometers up, it's going to be a few meters wide, if it is still bright enough to be seen. So therefore, it is for laser beam, if it is limited by diffraction, the spot actually can be quite big if the distance is big. Alright, so let's take a look at another case, which is a very popular case that is asked in IB exams. So we talked about cars just now, so let's see. Our objective is to find the maximum distance of the car such that you cannot see the two headlamps as two separate headlamps. So let's assume that the headlamps are separated by about 1.2 meters. The distance to the headlamp is L, and your eyes are the ones looking at it. So this is the aperture, this is the opening. Let's assume that it's about 3 mm again. The wavelength of the light coming 600 nanometers. So therefore, when the point of being just resolved, remember the angle subtended by the objects, which is x upon L, must be equals to 1.22 lambda upon d. This is the opening size. This is the distance to the objects. And this is the distance between the objects. So given this, what we want to find is L. And if you plumb in all the numbers over there, you should be able to find L as 1.2 times 0.3 to the power, not 0.3, 1.2 times 3 to the power minus 3 divided by 600 nanometers. You'll find that it is a nice number. L will be 6,000 meters away, which is 6 kilometers away. Now, if you are staying somewhere near school at 121 Dover Road, that means 6 km away probably is all the way to Vivo City or even further. So that's actually quite far. But we know that we wouldn't be able to see two objects as two objects, two headlamps as two headlamps that far. It will be nearer because there is something called air in between us and the object. So the air actually causes some disturbances and reduces that maximum distance. Alright, so let's recap what are the most important things in resolution. You got to know Rayleigh's criterion. You must know how to state Rayleigh's criterion, that the minimum separation or the condition where it's just resolved is when the first central maxima of one source meets the first minima of the other source. And you must be able to apply a simple calculation like this. Be careful when they ask for diameter, must times 2 because it's above and below. And for this one, very common question. You are given two objects, usually 4 parameters, 1, 2, 3, and 4. And usually you'll be given 3 and asked to find the other one. Okay, so take a look at the examples in the notes and the questions. Give it a try and see if there are any problems. If there are any problem during our e-consult, feel free to raise it up. Alright, all the best.